Okay, this is problem 10.47 in your book. Calculate the density of nitrogen dioxide gas at 0.970 atmospheres and 35 degrees Celsius. Just first, a little note, density for gas is going to be grams per liter. So you're thinking, well, if I did this for 1 mole, then all I need to do is figure out how many grams in a mole, and then I know that an ideal gas has 22.4 liters per mole, so I could just divide that by 22.4 liters, and I get grams per liter. Well, that only works at standard temperature and pressure, which this problem is not. So we need a way to calculate that if it's not at STP. So we can use the ideal gas equation to calculate the density. Remember that N is moles, and moles are equal to grams divided by the molar mass, or in other words, mass divided by molar mass. Capital M then stands for molar mass. Alright, so then I can rewrite the equation. Instead of putting N, I can put PV equals mass divided by molar mass, RT. And then knowing that density is going to be grams per liter, density of a gas, or mass per liter, I notice that I've got mass here and volume here. So if I get mass over volume, that's going to give me the density. So to do that, I can multiply both sides by the molar mass, and then divide both sides by RT. Let me try that again. Alright, I'm going to multiply both sides by the molar mass, and then I'm going to divide both sides by the volume. There we go. And you'll notice right here you've got mass over volume, which is density. So then, if I divide both sides by RT, molar mass times the pressure divided by RT, alright, is going to equal mass per unit of volume, which is the density. Alright, so let's try the next page here. Density equals MP over RT for 1 mole of NO2. Alright, so we're going to get the molar mass for 1 mole of nitrogen dioxide is about 46 grams per mole, times the pressure they gave us for this was 0.970 atmospheres. Alright, and then we're using atmospheres and kelvins and moles. So our gas constant 0.0821 liter atmospheres per mole Kelvin. Alright, times the temperature, which is 35 degrees Celsius, so 273, 83, 93, 03, so 308. Alright. So when I turn this, the kelvins are going to cancel here, and then grams per mole, and then this mole here is on the bottom, so this is going to cancel. Alright, and then atmospheres here and atmospheres here is going to cancel. So notice what we're left with is going to be grams per liter. Alright, so if I multiply those out, so we get about 1.76 grams per mole to 3 significant figures. If you took the molar mass, 46 grams per mole, divided it by liters per mole at STP, you'd get about 2. So you can see with the increased temperature and atmosphere coming down a little bit, I get less density than I would at STP.